Hey everybody, welcome back to chemistry. And so in this presentation, what I want to do is describe something called Ka. So what Ka is a way of quantifying the strength of acids. In particular, we like to use this value to quantify the strength of weak acids. So this value will tell you how strong a weak acid is. And so can I increase the slide just for a second? So what I want to do is I want to show you how to write expressions for Ka. And so what I'm going to be doing is I'm going to be focusing on acetic acid, and you can see it has a Ka value here of about 1.8 times 10 to the negative 5. And I want to compare that to hydrocyanic acid, which has a Ka value of about 6.1 times 10 to the negative 10. So if I can decrease the slide. Okay, so first let me go ahead and write the reaction describing how acetic acid reacts with water. And so the formula for acetic acid is HC2H3O2, and it'll react with water. I'm going to put the arrows here in just a second, and you'll get hydronium and acetate, like that. Now, one of the things you might remember is that acetic acid is a very weak acid, and so when you prepare most acetic acid solutions, you will have mostly reactants. And so to remind myself that we have mostly reactants, I'm going to do the arrows like this. The forward arrow is like that, but the reverse arrow will be longer. And so this will remind me that this is a weak acid. Again, most solutions will have more reactants here than products. You can say that the reaction is shifted to the left. All right, so let's compare that to hydrocyanic acid reacting with water. So here is hydrocyanic acid, HCN, reacts with water. And so to do so, the hydrogen ion will break off, stick to the water. It forms hydronium plus the cyanide ion. Yeah, that's the one that's extremely dangerous that you want to stay away from. So this reaction for a hydrocyanic acid, this is even a weaker acid reaction. And so you're going to get even fewer of these products formed than, say, you would get for acetic acid. So how would I indicate that by arrows? Well, I have a forward arrow like this, but to indicate that this hydrocyanic acid is a much weaker acid than acetic acid, I'm going to draw this huge reverse arrow like that. And so this is a good reminder here that hydrocyanic acid is a very much weaker acid than acetic acid. So at this point now, what I want to do is for both of these acids, I want to write an expression for K, and then I want to write an expression for something called Ka. So first K. So K, you may recall, is the concentration of the products over the reactants. So who are the products here? So the products are H3O plus, and so we put the name of the molecule in brackets to remind ourselves that we wanted the concentration of the hydronium, and then we have the concentration of the acetate, C2H3O2 minus. Okay, then this is over the concentration of the reactants, which is going to be acetic acid, HC2H3O2 times water. Okay, so that is a good expression for K for this reaction. Let's do one here for this reaction. So we could have K for this reaction as well. And so again, it's products, which is hydronium times cyanide over HCN and water. Okay, so far so good. So these are good expressions for K. Now, let me go ahead and write an expression for Ka. It's a little different. So now we're going to write an expression for Ka. So it's basically K with a little a. A means that this is an expression that that you can write specifically for acid reactions. So here we go. Again, it's products over reactants, but with a slight change. And so it's products hydronium times acetate over reactants. But here we do not include water. We just include the acid concentration. So again, we leave out the water concentration and just have the acid concentration. I'll talk about why we did that in a second. Okay, you can do the same thing here for this acid here. So I'm going to write a Ka for this acid. So it's going to be products, H3O times the concentration of cyanide over, again, for reactants, we leave out water. So it's HCN. So I think one thing you can see immediately is that when you calculate a value of K for this reaction, it's going to be a little different than the value of Ka. And the reason is when you're calculating a value of K, you include the concentration of water in the denominator, but when you calculate the value of Ka, you do not include the concentration of water. So that will make the value of Ka a little different than the value of K. And so this is true for any acid you deal with. And so you might be wondering, well, why do that? Why leave out the concentration of water? And the reason is what chemists like to do is they mostly like to compare the values of Ka. And one of the things you'll notice here in these expressions of K, you have water here in all the expressions. And water will have the same concentration no matter what different kind of acid you have in it. In fact, the concentration of water is 55.5 molar, and you can Google that to see how they calculate that. So what chemists do is they say to themselves, well, heck, since all of these expressions of K have a water term, let's simplify the expressions a little bit and just leave out the water term. And so that's what they do. So you can figure out what the value of Ka is for an acid by experiment. You would have to find some way to figure out the concentration of hydronium, the acetate ion, and acetic acid. And when that's been done, they put the numbers in and they get a value of Ka. So the Ka for acetic acid, I'm going to write ACA for acetic acid, is around 1.8 times 10 to the negative 5. There are no units here, and so let me remind you what a small number that is. It's 0.000018. Again, no units here. So now you can also do a similar experiment to figure out what the value of Ka is for hydrocyanic acid. So Ka for hydrocyanic acid is a much smaller number. It is 6.1 times 10 to the negative 10. And so that will be 0.000007. There we go. I think that is right. So you can see that's a very small number. So the thing that I really want you to see here is that the smaller the value of Ka, the weaker the acid. So if I can increase the slide. So here we have a listing of Kas for several weak acids. So notice that these are all weak acids here, and these are not strong acids. And so one of the things I want you to notice, again, as you go down this table here, you're getting a weaker acid. So as you go down the table, you're getting weaker acids. And then here, the value of Ka is getting smaller. So now what we can do is, let's try these questions here. It says, which is the stronger acid, acetic acid or hydrocyanic acid? So the way you figure that out is you look at the acetic acid and you see its value of Ka. And then you look at the value of hydrocyanic acid and you see its value of Ka. So we determined that as this number Ka gets smaller and smaller, the acid gets weaker and weaker. So here, as the Ka gets larger and larger, then the acid gets stronger and stronger. So between 6.17 times 10 to the negative 10 and 1.75 times 10 to the negative 5, acetic acid is the stronger acid. So it's this one. Acetic acid is stronger. Okay, next question. how does the strength of acetic acid compare to hydrochloric acid? And so I just kind of determined that acetic acid is stronger than hydrocyanic acid. But you have to remember, acetic acid is still considered a very weak acid. Now, off the chart up here is hydrochloric acid. So I'm going to write hydrochloric acid up here is a very strong acid. And when you have strong acids, you can have Ka values that are positive, exponent. And in fact, the Ka value for hydrochloric acid is 1.0 times 10 to the positive 7. So if you have a positive exponent for a Ka value, that means it is a strong acid. If it's a negative exponent for a Ka value, it's a weak acid. And the larger number of the negative exponent, the weaker the acid it is. Thank you for listening. We'll see you next time.